All right, okay, here we go with the lecture from, let's see, what is it? Today is 26th, but I'm going to post it as the lecture of the 25th, which is the day that the class would have met. Okay, now we have arrived at a point where I'm going to make a turn, right? We've been dealing with providing you with a sufficient appreciation for the process of system identification. Of course, a lot more could be said and in a course on identification itself. And I've given you, but you have sort of should have by now some sort of general idea of what's involved, and we've also have a little bit of practice on seeing how the results from identification, in this case frequencies in particular, which are the ones that we've been using, can be utilized, right, to improve finite element models, or sometimes even to locate changes in finite element models. But we've done it, of course, in simple cases of small structures where we sort of, are looking for one or two parameters that may have changed and so on. As you can imagine, the problem of damage detection in realistically sized structures, it's a difficult one, right? Because there's many parameters that could have changed. The models are complex and so on, right? So it's difficult to make a correct model or a good model, not forget about correct, a good model, even without the damage. So we normally are searching then for schemes that can, let's say, eliminate the need for a model if we can. At least if all we are interested in doing at this stage is simply to announce that there is or there isn't any damage, right? So, let's see, where is my thing? Yeah. So if we have damage, we may be interested in answering the question, or we are interested in answering the question yes or no, right? Is there sufficient change in the system so that we want to announce that damage is likely to have occurred? That's one thing. That's what is normally referred to as detection. Following detection, you might be interested in asking questions related to where is this damage, right? That would be a location problem. And then a third question might be how large is this damage? And that is a quantification problem. There is also the prognosis. What happens if I don't do anything at this point? Okay? The model updating approach is an all-encompassing one, because in a model updating approach, you find where is the damage, how large it is, etc., right? The problem is that to tackle the thing from a model updating perspective is actually very difficult unless the system is small, right? So we normally like to use, or not like, we normally rely on the divide and conquer strategy, right? Don't try to solve the whole thing on one shot. Let's just try to manage the question first. Is there any damage, yes or no? And let's see what we can do with that question. And it turns out that for that question, we can do quite a bit without having to complicate the situation with the need for a finite element model. So that's where we are going to be turning right now, to the problem of damage detection. Okay. Now, to discuss the problem of damage detection, let's looking for my other marker. Oh, here it is. Okay. So, to discuss the problem of damage detection, let us say that we have here our system, and that our system is subjected to some loading, right? Which this loading could be f, for example, functions of time. Our system name is omega. Our system then also has some outputs which we can call y, y1, y2, y3, etc. And as time passes, let's say this is the reference state, right? When we know that the system is healthy. Now time passes and we are here at a different time. And then this is omega at the time of inquiry, right? At the time of inquiry, the structure is subjected to another set of loads. Let's say these are called FR, and these are called F at inquiry, right? These are functions of time. And if this is Y at reference time, we also have some Y's at inquiry time, right? And we have a question here, which is there damage? Has this structure changed sufficiently for me to worry about it? Now, if things were perfect, if there was no noise, if we could actually measure things precisely, this problem would not be that difficult, right? Because we could use our knowledge of the, let's say, the input and the output in the ideal case. And from this we could calculate, let's say, the frequencies, right? Now we come here and we measure the inputs and the outputs again. We do system identification and we get the frequencies again. If the frequencies, some of them, are significantly different, we say there is damage, or even if they're a little bit different, right? So that doesn't seem to be so hard from that perspective. But what happens is, however, that we can't calculate these frequencies with such precision to make a distinction just because it changed by a little bit. And the structure is also, we have to remember, affected by the environment. So, what I mean by the environment is that maybe when we took this reference data here, the temperature was 40 degrees. And when we are doing inquiry here, the temperature was not 40 degrees, was 80 degrees. So the structural properties may be somewhat affected by the change in temperature. And so we see a frequency shift, or, you know, and it's not really due to damage. So that's one complication. The environmental changes makes the comparison of the two cases different. There's another issue. Many times we cannot know the load. That is, these loads are from ambient sources, wind, traffic, etc. So if the loads are from ambient sources, we can do a stochastic identification, right? We can do stochastic ID, but at the point that we do stochastic ID, which you just recently learned, we can no longer get the frequencies so precisely as when we can measure the input, because this theory of a stochastic identification is based on expectations, right? So expectations means that for an if we are measuring something, right, we need to have a situation that is stationary. That is, the statistics should not change in time. And we also need as long as time as possible for the expectations, the averages, to work. So, on the one hand, you could say, I am patient. I'll just take a really long time so that my expectations will be quite accurate. And in fact, that is a good idea, to take a really long time. But you can't take so long a time that the system is no longer under the same environmental conditions. For example, you could not take, 15 hours of data and expect that the winds and the environment and so on was more or less the same. So now you are actually violating the assumption about the fact that the sources are not changing during your measurements, right? Therefore, we have to do a trade-off, right? So we measure the data for a long span in order to improve our computations, but we cannot make that span 15 hours or something, right? So maybe we can make it half an hour, sometimes even 1 hour has been done. So we go back to the fact that when we do the healthy state, let's assume that you have an axis here, which is, let's say, how do I do this without complicating it necessarily? Let's say this is the real and this is the imaginary. And as you know, the eigenvalues of this have a real part and an imaginary part, and we know that they are related to frequencies, which is frequency times the damping plus or minus omega damped I, right? That's how you extracted your frequencies when you do system ID. So let's say we take a look at one of those eigenvalues and you do one test, you get it there. Now you come back tomorrow, same time, same station, and you do it again, right? Temperature was about the same, but you don't get the same number, you get another number. And if you do that for a long time, you get many numbers. What you find is that this thing that you call the frequency is something that you really can't calculate exactly. It's actually some sort of a ball, right? Now my scale may not be correct there, but the point is it is not a point. If it were a point, it would be very simple to know if the point has shifted. But what it is not a point, it's a little ball, right? So when we come here 1 year later and try to determine if there is damage, we know that there is a certain ball where this frequency normally lies, even when the system is healthy. Now, of course, if we now calculate that frequency and it turns out to be here, there isn't any concern, right? That one is pretty clear that it is a damaged case in the simplistic view, right? You can realize, of course, that the system could have been this day around here and then the damage moved it from here to there and it's still on the ball, right? So this is the effect of the damage. So this is the initial point and the final point. This is a way that we idealize it in our head. It's sort of like saying, imagine first that the damage did not take place. Given the environment and the noise and so on, when I did, where would I get my point? And you might say, okay, my point would have been in this eye. Now let me the damage appear instantaneously. Where would it go? It goes to here, my F point, right? Well, it may be that your F point, you were unlucky. Your I point was on some sort of an edge of the ball and the damage moves it in a direction that it stays within the ball, right? So it is not a trivial problem to identify damage, right? Because of variability. The smaller this ball gets, right, the more accurate that, the easier it is to detect changes, right? Now, let me see. So the smaller the ball gets, the easier it is for you to detect changes. And one way that, you can do many things to try to make this ball smaller. And as I say, one of them is, or not one of them, the typical approach would be try to get data under similar operating conditions. So you are computing the frequency when the temperature is between this and this, right? And in days where there is sufficient wind or sufficient excitation so that you're not operating with minuscule amplitudes in which the noise could be more of an issue, right? But the point is then that at this stage at least, all we want to do is to appreciate that damage detection is a statistical problem, right? It's not a deterministic problem in which you just say, oh, this should have been 2 and it's 2.05 and that's it. The thing that you are using to characterize whether there is damage or not is a fluctuating quantity. Okay, so that takes us then to the fact that if we want to work rationally, we have to work in the domain of statistics for the problem of detection. Well, I shouldn't say we have to, but a statistical approach, a probabilistic approach is the correct framework, and this framework, we want to use it without having to formulate a precise finite element model of the structure. Okay, so let's then assume, or not assume, let's then operate like this. Let's say that we have data that we collected over and over and over, and that after plotting all the data, we find that a Gaussian distribution is not a poor guess for how that frequency is distributed. I'm going to look now at the univariate case. Meaning a single frequency. Next, not right now, but next, we will be getting this thing to a more realistic situation where I can say I was able to identify more than one frequency, right? But right now, let's just say I was able to identify one. So I have one frequency, and after I after I calculate that frequency, let's say omega, I calculated omega one time, no, I shouldn't say, because 1 and 2 and 3 is going to appear as if it's a different frequency, right? So omega was calculated many times, right? And from those many times, we can do whatever we know how to do to try to see what the probability distribution of that quantity is. And most of the times, it's found that a Gaussian distribution is reasonable, right? Now, a Gaussian distribution is characterized by the mean and by the standard deviation, right? So we could take our data, which I think in this case I'm going to use x, because that's how I did it as I was preparing the notes. So x could be the frequency, but let me just use x for the variable, right? So we could calculate the mean, and we would say that that's the mean, right? And we could calculate the standard deviation, and that would be sigma. Now, of course, our data is not going to be a perfect Gaussian, and we're never going to have enough data to plot this thing, for thousands of cases. We just have, I don't know, maybe, if you're lucky, 100 cases or 200 that you've done over 1 year at reasonably the same temperature and so on. And from that, you can see, okay, the Gaussian doesn't look so bad. We know that from the get-go. And you can then calculate the mean and the standard deviation and replace your idea of the data simply by the idealized curve, right? So that is the distribution that we are assuming is our system in the healthy state. Now, we want to make a decision as to what is, we get a new point now, and we want to know if that point is healthy or unhealthy. Because it's Gaussian, there is always, in theory, right, the probability that this could be anything in any direction, but obviously if we get a point right here, we know that is so unlikely that has to be damage, right? We do not ever expect to get points on this side that way because our damage does not tend to increase the frequency, right? So if this was frequency, we would not expect to get damage to move the thing to the right because the frequencies are not, it's not going to go up, it's going to go down. Okay, now the question is, should you use this value or this? What is your limit? So let's say that we take this limit and we call that XC to be the critical. Now, this area here, which is how much of the distribution is to the left of XC, is what we call the type 1 error. Or the error type 1. And it is typically and often taken to be 0.05. That is, we know that under distribution, probability density, the area is 1, right? Because there is a 1 probability that the value is something. We are sure that it is something, right? Now, if we take XC so that 5% or 0.05 is the area under the curve on this way, why do we call that the type 1 error? Because we make the following decision. If we measure any day X to be less than XC, we announce damage. Okay? If we measure any day later on, right? This was done on year 1 when we were creating the model. That's it. We've got the Gaussian. Now we decided, okay, it's over. We're now on an investigative mode, inquiring mode. So when we collect data now, it's not to make a model, it's to ask the question, is there any damage? So we get an X, and the X today was this value. That's fine. This value, this value. At which point are we going to say that X that we just got, or that frequency, is so weird that we're going to assume that there is damage? Notice that we don't know what happens when there is damage at this point, right? We just know what happens when there is no damage, which is the reference model. Now, if this is 5%, what that means is that the probability that we get a value here in this range, right, even though there is no damage, is 5%, or the type 1 error, right? So the type 1 error is called the false positives. So it's the probability of a false positive, because there is a 5% chance, or a type 1 error, if you want to use a different number, chance, that the structure is not damaged, but that you do get a value over there, because every once in a while something weird happens, right, in the data. And in that case, you will announce that you think there is damage, but there isn't any damage because we are agreeing that nothing has happened. Therefore, this is the type 1, this is the percentage of false positives that you will incur. Now, so I'm going to take this, erase it here. Now, even though we do not know what happens due to damage, we do know, or we do expect, that after damage, the probability distribution of the system in the damaged state, assuming that damaged state is staying constant, it's on the left. In other words, the whole thing shifts this way somewhat, right? And so we have a new distribution. That could be like that. So this is the reference, and this is the damage. So for this damage state, you would say there to make it a little clearer. Okay, that was the mean. And this is the critical, and that's the type 1, right? That we decided on. Now, if we decide on that on type 1, what happens if we get a value that is, let's say that the system is in fact damaged now. Of course, we don't know. So the system is now damaged. We collect data today, and we find the x, and our x proves to be here. Actually, I shouldn't even take it up there. I just say this is the value. So that value is to the right of xc, right? And we don't know. So this is a value that we say there's no damage, right? Because we only call damage things that are bigger than xc. So we say no damage, right? But in fact, the structure is damaged. Therefore, what we see is that whatever is to the right of xc, which is this part here, is what's called the type 2. That type 2 error means that the structure is actually damaged because you're in this distribution, but you don't announce the damage because it's less than your count, right? So the type 2 is the false negatives. That is, you do not announce damage, although damage is actually present, right? So those are the two types, type 1 and type 2. Type 1 is false positives, and type 2 is false negatives. Now, the area in the damaged state is of course also 1, right? So the remaining area here is your chances of finding the damage, right? So that's called the power of the test, POT. And you can see from the sketch that the power of the test is 1 minus the type 2. Okay? So this concludes this discussion here. I will erase it to take some lines off and kind of draw it again to do something more, some more technical things on it for the next stage. But right now, let me quickly go over it one more time before I erase it. From data that we collect over some time, we postulate some probability distribution that governs our quantity, which in this case is a single number, and we're assuming for discussion it is a frequency. In principle, it doesn't have to be Gaussian, it could be any distribution, but it can be shown that the Gaussian distribution makes a lot of sense, and when you actually empirically look at it, you do find that the data tends to match the Gaussian quite well, and there are good theoretical reasons for that, and so we get something. Now, we do not get this curve empirically. We actually, plot it. We take the data, and from the data, we compute the parameters of the Gaussian distribution, which are the mean and the standard deviation. And then we replace the data by the idealized curve, right? Now, once we have the idealized curve, we say, okay, what are we going to call weird? And we decide that we're going to call weird or unexpected anything that is to the right of xc, to the left of xc, right? Such that the area to the left of xc is what we call the type 1 error, right? And the type 1 error is a false positive because it means the structure really wasn't damaged, but if we find something here, we call it weird, and so we call it damaged or strange. And that type 1 error is typically taken to be around 5%, right? You need to make that cut somewhere, because if you don't make that cut somewhere, then it's impossible to find any damage, right? If you said it was 0.000001%, then XC would be here, right? And so that means that almost anything is okay, right? So you take an XC and you say, okay, I'm going to let myself 5% probability of making a false negative. I mean a false positive. Right? Because the point was here, the system was undamaged, but I called it damage. Now damage takes place. And because damage takes place, the distribution shifts to here. Right? So this distribution moves to here. That's what the damage did. It moved it. We typically assume, by the way, that the damage shifts the mean but does not affect the standard deviation. That is not a theoretical statement, but it is an assumption that is made almost universally and that is reasonably well satisfied. So now the distribution, the damage has shifted to here. Now once the damage shifts to there, then we say, okay, where does XC fall? We don't know where this is, so this is just a description in terms of imagine that we knew it. So if the XC is read here, then we see that the distribution has a right side. And that area under there is an area where if we get values after the system is damaged, we would say it's not damaged, right? Because we still think that we are in the first distribution. And so that area that shows up over there is what we call the type 2. And it is therefore a false negative. We say no problem, and in fact there was damage. The power of the test being what's left of the distribution, and it's 1 minus the type 2. Okay? All right. So now let's erase. Postulate again the same sketch without all the lines. Okay, so this is the reference stage. This is some damage condition, right? This is the mean. This thing had a standard deviation. Now, this is the new mean, right? And this is the point XC, where this was the type 1 error. Okay. Now, the first thing I want to note here is how far did my distribution mean shift due to the damage. It shifted, sorry, the distribution shifted its mean from here to here. Now, that distance is going to be approximately, if it's not too big, if the damage is not too big, is going to be approximately equal to the derivative of x with respect to the parameter that produced the damage. I'm assuming that in this case that there is only one in order to make this sketch, right? Multiplied times the change in the parameter. So this is using a straight line or a first term of a Taylor series. I could have done it assuming that there are more parameters. Then this would be a horizontal row times all the parameters. But there's no need to complicate it mentally right now. You can just think about there being a single parameter. It's all the same thing. I mean, it's the same for the purposes that I have at this point. Now, what I do want to do, however, is to change the notation to start getting our mind used to it and just say, let's call that which again when we go to multivariate is going to be the Jacobian. Let's just call it J, okay? And so that is J times delta theta. Eventually J will be a matrix, delta theta is a vector, but right now J is a number, delta theta is a number. That's how much this thing shifts, right? Now, in order for me to determine XC, what determines XC? XC is determined by this thing here, which is called a type 1, right? And that distance here, we can call it alpha 1 sigma. That is, you need so many standard deviations to make sure that only 5% of the data is to the left, right? You need, I repeat, if you want, you might want to remember this, right? If you have a Gaussian distribution with zero mean and unit standard deviation, that's what people call the standard Gaussian, right? So we know that as you move away from this thing, there's less and less area that's left, right? So if we want to know that this area here, which is really the same thing as this area here, is some fraction, then that requires that we move alpha 1 times sigma, which is 1 in this case, right? And that will make this whatever we want, and there are tables to find what this is depending on this, or even better, in MATLAB, that is something that one can do very quickly, because the command would be, let's say that's type 1. So if I was in MATLAB, or if I were in MATLAB, I would simply say alpha 1 is equal to norm INV, that is the inverse of the normal cumulative distribution, parentheses. Then what I want to know is the area in which, so I would say, well, maybe this will be clearer. 1 minus type 1. And if we have type 1 equal to 5%, that would be 0.95, right? So basically I'm asking MATLAB to tell me how far in standard deviations do I need to go so that 95% is on the left in a distribution for which the mean is 0 and the standard deviation is 1. You should go to MATLAB and get help norm inv to understand that command, right? This is the mean, this is the standard deviation, this is what you want the area on the left of the distribution to be. So if I want the area on the left of a distribution of 0 mean and 1 standard deviation, or unit standard deviation, that command tells me what it is. And in fact, it turns out that that's equal to 1.6449 for type 1 equals 0.05, okay? Just so that we have the value. So for type 1 equals 0.05, alpha 1 is 1.6449, which means you have to move that many standard deviations to the right in this standard distribution so that 95% of the area is to the left. Okay? Needless to say, if this is the data not shifted to the center or anything, and this is the mean, how far do I need to move this way so I only have 5% left is simply alpha 1 times the sigma of this distribution, which is not 1, but everything is proportional. So this is where my XC is, right? Now that we know that, we know where our XC is, and we know that, well, we don't know, but we are saying that the mean of our distribution due to damage shifts to the left by the Jacobian, or the derivative of the x x with respect to theta times delta theta, then we can say that, let's see, the distance d shown there, which is the distance from the mean of my, I'll put it again here, the distance from the mean of my damage distribution to the XC cut is d, right? So let's see what d is. So d is equal to all this thing, and all this thing is x bar minus, what am I doing? All this thing is x bar minus j delta theta, x bar minus j delta theta is this, minus this part, which is alpha 1 times sigma, right? Oh no, I'm sorry. Yes, that's okay. But, so we can write it again. D is equal to x bar minus j delta theta minus alpha 1 sigma. But alpha 1 sigma is equal to x bar minus xc, right? So x bar minus xc is alpha 1 sigma. Therefore, we find that the distance d shown in the graph, the x bars cancel, and it's equal to xc minus j delta theta, right? Okay. Now, let me see, xc minus j delta theta. Okay, let me erase here, so I can have some room to write it somewhere. So d, again, is xc minus j delta theta, but we can write xc as what? xc is equal to x bar minus alpha 1 sigma, right? xc is x bar minus alpha 1 sigma. Therefore, we get x bar, seems like this was repetitive. Wait a second. Let me just see which way, because I may be going around the loop here without any need. Yes. Yeah, I guess everything was okay. Maybe I repeated something. But D, this D, right, is equal to x bar minus x bar minus j delta theta minus xc. So it's just that I wrote the order here differently. No, there's something wrong. Let's look here again. Yeah, this D is correct. This point here, this point here is this point, which is x hat minus j delta theta, right? That's this point here. This is xc, and therefore just erase so I don't screw what I've done. I did it in clean here and then I got messed up here. So sorry. So let's see. First, as far as the sketch, this is the mean of the undamaged distribution. This is the mean of the damaged distribution. This is the critical point that defines our type 1 error, right? The distance between this and this I call d. Now, this point moves to the left by the Jacobian times delta theta, so this point is x bar minus the Jacobian times delta theta. That's clean. That's this point, right? Therefore, d is equal to xc, which is this point, minus this one here, right? Minus x bar minus the Jacobian times delta theta. Okay? Now, x bar, or xc, is equal to x bar minus alpha 1 sigma. So let's see. xc, which is this one, is x bar minus alpha 1 sigma, right? So you go back like this and you're there. Then we substitute this here and we have that d is equal to x bar minus alpha 1 sigma minus x bar plus j delta theta, right? Therefore, we find that d is equal to, these two things cancel out, and so we get j delta theta minus alpha 1 sigma, right? Okay, that's it so far. I think I had that before, but anyway, so that's the distance from here to here. Now, what we need to do is to say, if I move d away from the center or from the mean of my damage distribution, how much area is there on that side? So imagine first that we look at the standard once more, right? The area that is to the right here, that's the type 2, right? That's the area to the right of xc in the damage distribution, that's the type 2. So imagine that I come here where the mean is 0 and the standard deviation is 1, and I say, okay, this is the type 2. How far do I need to move in order to just have something that I want over the, well, I shouldn't say that I want. What is the relationship between this and type 2? So for that, we can say that alpha 2, which is the same way as before, is the norm INV of 1 minus the type 2, right, comma, of a distribution that has 0 mean and 1 standard deviation. So that's our alpha 2. Then we can say that, where is our d? Here is our d, right? So my d divided by s, my d divided by sigma, if you want, in terms of this, in terms of standard deviations, is just j delta theta over sigma minus alpha 1, right? But I know that the d over sigma can be related to the type 2 by alpha 2. So what I want to do is to have this to be alpha 2, and this is j delta theta over sigma minus alpha 1. Therefore, J delta theta over sigma is equal to alpha 1 plus alpha 2, and that's where I wanted to go at the end. Because what it means, let's see. So let's focus on that. J delta theta over sigma is alpha 1 plus alpha 2. And I guess I should draw this here so I can review it for you guys. This is alpha 2, this is type 2, and this is 0 and 1. Okay. And this is, to be redundant, type 1, and this is alpha 1. Okay. So alpha 1 is how many standard deviations you need to move to the right to arrive so that this area on a normalized distribution is type 1 error. Alpha 2 is how much you move to the right so that this area here is type 2. Okay? And what we find is that there is a relationship by looking at this geometry that now what is J delta theta? J delta theta is the shift of the mean, right? The mean due to damage shifts from here to here. This is the shift expressed as a fraction of standard deviations. So the shift expressed normalized to standard deviation happens to be alpha 1 plus alpha 2. Okay? Now, let's say that we want to make it now concrete. Let's say that we want alpha 1, no, let's say that we want the type 1 error to be 0.05. Therefore, alpha 1 works out to be 1.6449. Now, alpha 2 depends on what? Alpha 2 depends on the type 2. I know this is confusing because type 2 error, you don't know the distribution of the damaged case. But what we have to say is, let's assume that I am not satisfied unless I have a power of the test of, let's say, 80% or 90%. So power of the test is equal to 1 minus the type 2, right? So the power of the test is that. So let's say you want a power of the test. Let's say you want a power of the test of 0.8. So you want to have 80% probability of announcing damage correctly if the damage has taken place. That is, you want 80% chance to be here when damage takes place. Now, if the power of the test is going to be 0.8, that means that you want the type 2 to be 0.2, right? So you can go in here and put 1 minus type 2, 0, 1 and find alpha 2. And in that case, what you find is that alpha 2 is, let's see, I thought I wrote it here, but I guess I did not. I have it somewhere else. Gosh, where did I put it? Sorry. All right. Since I do not find it, what we're going to do is you're going to give me a break and I'm going to go in here in MATLAB, which I'm looking at it. You can't see it, but I'm looking at it. I'm going to say norm inverse, and then with type 2 being 0.2, it would be 1 minus 0.2 would be 0.8. So I would be putting 0.8, 0 and 1. And I would find that alpha 2 is 0.8416. Okay. So I just went to MATLAB and I typed this, and I got alpha 2 to be 0.8416. Okay? So now we can go and substitute over here. And I'm going to have to erase here. You already been looking at this for a while. So I have some room. So we have that J times delta theta divided by sigma would have to be alpha 1, 1.6449 plus alpha 2, 0.8416, right? Remember, this is alpha 1, this is alpha 2. This depends on the type 1. This depends on the type 2, right? Now, if you sum the two of them, which I'm doing here, you get 2.49, okay? So J delta theta over sigma is 2.49. And we arrived. That's the whole point after all this. What does this mean? It means that if you hope to have a power of the test of 80%, your damage must produce a shift in the mean, which is at least 2.49 times the standard deviation. Out of the way here. And let me repeat that in words. So, okay, so J times delta theta over sigma equals alpha 1 plus alpha 2, okay? Here it goes. Here is the standard, the Gaussian distribution in the reference state. Here is the Gaussian distribution in the damaged state. This is the reference state. This is the damaged state. Of course, the reference state is only one, right? The damaged state, there's a million damaged states. So this is one of them that we're looking at. Now, when we select the type 1 error, that gives us this point, XC, right? And that point immediately gives us this, right? Now, how far this is moved, how far the damage has moved this to the left is just J times delta theta, right? So, that's it. Now, what we say is the following. If you want to have a type 2 error of a certain amount, then you need to have that alpha 2. And you therefore will have a certain alpha 1 plus alpha 2. And then you can say that your J delta theta must be greater than or equal to your alpha 1 plus alpha 2 times sigma. And for the case where we have type 1 5% and type 2 what did I say, 20%, right? So the power of the test is 80%. So if we want to have a power of the test of 80% and we want to have only 5% probability of giving false positives, then the damage that we can detect with that kind of a power of the test has to produce a shift in the mean of no less than 2.5 times the standard deviation. For this particular case, right? So if your damage does not produce at least 2.5 times the standard deviation, you will not have that much power of the test, you'll have less. Okay? So what this tells us right away is how important it is for two things. We want to use things that will move quite a bit due to damage, right? So if J is big, it's easier to satisfy this, right? So we want high Jacobians, high derivatives with respect to the parameter. We want J to be large if we can. So how can we make anything? Well, at this point, all I would say is, let's say that you have 3 frequencies, the first, the second, and the third, and we're only going to use one. Then you would maybe ask, which one do you think is going to shift more when we get damage? Do you think the second one is more than the third? Okay, well, whatever. I don't want to make an argument in one direction or another. Let's just say that we assume that the second one is going to be the one that's going to shift more. So let's use that one because we get a larger J. Now, from another point of view, what is it that will help us find the damage? Small sigma. So we want to select a frequency, again using just one, that has the smallest standard deviation possible. So, because in order for us to confidently detect damage with that much power, we need to satisfy this requirement. Okay? That's the end of this first section. What we need to do subsequently is to generalize this now, to complete this module if you'd like, to generalize this to more than one frequency. So instead of using only one thing, we need to use as many as we'd like. So our feature is not necessarily a number, but a vector, which could be, let's say, frequency 1 and 2 and 3. So we would not talk about x being a number, but x being a vector. So we have to go to multivariate Gaussian distributions and a number of other complications. But let me close this unit by just saying that there is something used in the literature. You now learn the concept of type 1 error and type 2 error and power of the test, right? So type 1, type 2 and power of the test hopefully are clear by now. There is something else which is called the ROC curve, and that's called the receiving operating characteristic. It's called the ROC, receiver operating characteristic curve. That curve simply plots the type 1 error over here and the power of the test over here, which is the same thing, of course, as 1 minus the type 2. Right? And that curve, let's see, whatever it is, that curve depends on how many standards deviation is the J theta. So I don't know if that's clear or not, maybe not. In order to be able to plot this curve, you have to assume, right? What is your J theta? So, and that would be, 1, 2, 3, 4, 5. And this plot, power of the test versus type 1 for n numbers of standard deviations of the curve, is what's called the receiving operating characteristic curve. I personally don't use it, but it's so widely mentioned that I figured I would bring it to your attention. You can go and Google and take a look at it over there if you like. We are not going to use it any further. Let's see. So let me erase everything. And in fact, let me stop the module at this point, see how much time there is, and also to avoid the problems of uploading